All right, everybody. Welcome to the first lecture of the Principles of Stratigraphy course, 4750, 5750 for the semester. Today, we're going to sort of start in the upland regions and where the sediment comes from, and we'll talk a little bit about the processes that result in the production of sediment that can then be delivered into the transport systems, which can then ultimately become deposited. This course is going to follow a bit of a what we would call a source to sink structure, in a sense, where we'll start with where the sediment comes from, how it moves, and how it gets deposited, and ultimately how we can read the stacks of deposited sediment. Okay. So today we're going to be talking about weathering and sediment production. There will be two lectures today. The first, we'll talk about how the sediment gets produced on the landscape in place through the processes of physical and chemical weathering. And then in the second part of the lecture, we'll talk a little bit about erosion and the movement of sediment from the weathering site. And that'll sort of lead us into the next stages of sediment transport and so forth. So weathering is comprised of the processes which decompose and break down rock material. Okay, that's the basic definition of weathering, and it's distinguished from erosion in that weathering is the processes that occur in place where the rock sits. Essentially, it's the process that takes a large piece of rock and breaks it into smaller pieces of rock, right? Or dissolves it by fluid interactions and so forth. Whereas erosion is then taking that broken down or dissolved rock material and moving it away from the site at which the weathering occurred. Okay, so those are the two sort of distinctive processes that we will cover in the two different parts of today's lecture. All right, so we'll start off with weathering here. There are two main types of weathering processes. The first is mechanical or physical weathering. This refers to the breakdown of rock into smaller pieces by the processes of abrasion, cracking, and so forth. And this is the processes that occur without changes in the chemistry of the minerals themselves, right? So the rock pieces are not changing their composition, they're not changing their mineralogy or their structure, or their chemical structure, I should say. Whereas chemical weathering processes involve the breakdown of minerals by chemical reactions. Oftentimes on Earth, in the surface processes world, this occurs by way of chemical agents such as water or the things that are dissolved in water, like carbonic acid, for example. And so we'll cover both of these in today's first part of the lecture. And both are very important processes, depending on where you are and what the climate is like and so forth. And in fact, from global scale estimates, it's shown that they are approximately equivalent orders of magnitude here. So you can see that physical weathering contributes about 5.6 times 10 to the 15 grams per year. So that's a huge quantity, right? And chemical weathering is approximately the same. I would say that those are equivalent within the uncertainty of those estimates, right? But what's really important is that these two processes are not evenly distributed over Earth's surface. Some regions experience significantly more physical weathering, some regions experience significantly more chemical weathering, and some are lower or higher in total on that scale as well when combining the two together. Okay. So we'll start off by talking about physical weathering and the processes that break down rocks into smaller chunks, right? And one of the first things that I want to mention about this is that the processes of physical weathering, breaking down rocks into smaller pieces, can also promote chemical weathering as well, in the sense that if you take a 2 centimeter by 2 centimeter by 2 centimeter cube of rock here, for example, and you break it down into smaller 1 centimeter by 1 centimeter cubes, you are dramatically increasing the surface area that is available for chemical reactions to take place. If you imagine water flowing over this, right, this is a 4 times, I believe that's 4 times 8, sorry, 4 times 6, so that's 24 square centimeters, whereas this is going to be 1 times 6 times 8, right? So that's going to be 6 times 8 square centimeters of, so that's 36, 42, 48 square centimeters of total surface area for the same amount of volume, right? That can then be interacted by water carrying solvents like carbonic acid, for example. Okay, so the process of physical weathering and breaking down of rocks can really promote and make more surface available for chemical weathering as well. Okay. Physical weathering processes are generally considered to be dominant in colder, higher relief regions. So if you're in a glacial or an alpine setting, for example, you're more likely to have your weathering processes dominated by physical processes rather than chemical processes. But there's a significant additional amount of influence from things like the composition of the rock that you're weathering, the grain size of the rock matters, the structural fabric of the rock, whether you have fractures or joints. All of those inherent rock properties also influence sediment production, as well as things like weather and climate. And we'll talk a little bit about some of the processes that can result in physical weathering here. So in this particular image, you can see a glacier coming out here, and all of this till that's being deposited at the front of this glacier is the product of physical weathering of this rock here, right? This is a Schoolroom Glacier in Wyoming, I believe. And you can even see the beautiful light blue, powder blue color in the water here in this little pond or glacial lake here is glacial flour. It's very finely ground up silt that is produced by the physical weathering process of this glacier itself, right? So some of the processes that we can discuss that some of the physical weathering processes that we can talk about include exfoliation. This is a relatively common weathering process in plutonic rocks like granites, for example. And exfoliation occurs due to the release of the internal stresses that occur. So if you have a pluton that forms at depth, there's a uniform stress field that it is forming under, where the overlying rock is producing a stress that is balanced by an outward force, right, within that pluton, right? So these arrows are the stresses that are applied by the surrounding rock, putting pressure on the pluton as it's forming, and then so that is in balance with pressure inside that pluton, right? When you unroof that, when you remove the surrounding rock, say by erosional processes, as you're unroofing this pluton, then the stresses are no longer in balance, right? So there's outward stresses that are no longer being balanced by those, by the burial stresses. And so you end up getting expansion at the surface, and you get sheets of rock that kind of peel off. So that's called exfoliation. And here's a great example of that from Half Dome in Yosemite National Park, which has a lot of this type of weathering feature exhibited throughout the park. So you end up getting large sheets of rock that come off as part of that unroofing process. Another somewhat similar process that can occur in areas where there's a significant amount of temperature variation between, say, night and day, not like here in Louisiana, is called thermal expansion and contraction. And so if you have a boulder sitting on the surface, for example, and as the sun heats that rock, it expands a little bit, and then at night it cools and then it contracts a little bit, and that process repeats itself thousands and thousands and thousands of times every day and night. Over time, small joints will start to form in the outer part of that rock as it slowly expands and contracts over and over again, and they eventually will cause little flakes of that rock to fall off. So here's a beautiful picture of that, of a rock that's just sitting out there, and it's the dominant process that is shaping that rock is that thermal expansion and contraction. It's actually a measurable phenomenon. This is a really cool paper relatively recently where they put these little pressure sensors inside these rocks, and they measure the amount of expansion and contraction that occurred on a day-to-day basis. And you can see here that as the temperature increased and decreased as a function of the light intensity from the sun, the cracks would open and close and open and close and open and close. But over the long term, you can see there's a trend towards widening and widening and widening as that expansion and contraction continued over and over and over again. It's a pretty cool feature. You'll probably have seen similar features resulting from that in places like this is Colorado National Monument. It's one of the processes responsible for forming arches and things like that, or just these kind of rubbly piles that seem to just be jointing apart. Here's an image from Wyoming. So that's a relatively common physical weathering process in a lot of predominantly more arid regions that exhibit significant temperature variation between daytime and nighttime. There's also freeze-thaw. This is a pretty cool process where water can get inside pore spaces or fractures, and then in periods where it's cold enough to freeze at night, warm enough to melt during the day, the water can get into the cracks. It'll freeze at night, and when it freezes, it expands, right? And then during the day, that water is then melted, or that ice is then melted, and water can fill in that crack again. Then it expands a little bit more, then it expands a little bit more, on and on and on, right? And so you do this multiple times, you get rock that can seemingly just split right down the middle of these. You can see this in a lot of places where giant boulders are just split right in half. I'll show you a picture of that in a second. It's also responsible for things like frost heaving and stuff like that. So here's a great couple of examples of boulders that have just been split right in half. So it probably started as just a tiny little fracture. Maybe that fracture started as a function of other stresses or something like that, or maybe it was an inherent feature from from the previous stress condition of the rock. But as water got in there, it froze, it opened a little tiny bit, then the water melted, filled back in the crack with liquid water, then it froze, opened, and so on. And so you get these characteristic long linear cracks that form to break apart these rocks. Another physical weathering process is the process of abrasion. I think this one is relatively intuitive for most people, and it comes from the impacts or the grinding of moving other things, whether that be other grains of sediment or whether it be ice. Those can result in abrasion. So here's an image. This is an absolutely gorgeous satellite image of, you can see all this dust blowing off to the coast, or off of the coast here in Greenland. This is a heavily glaciated landscape. You can see the glaciers up here in sort of the upland parts, and those glaciers are abrading the rock material and grinding it away into fine silt here. And that fine silt comes down the river, it gets deposited on these floodplains, and then is blown away by the wind. The term for that fine glacial silt is called loess. LOESS here. And sorry, my dog is going crazy here. What are you doing? That's going to be a constant fixture through the semester, is my dog wanting scratches while I'm lecturing. So glaciers can cause abrasion. Wind can also cause abrasion by moving of sand. So when a sand grain gets picked up by the wind, it can move at incredibly fast speeds, right? You think of, wind can be, 50, 60 miles per hour, right? It can pick up a grain of sand and it can move it that fast. A grain of sand moving really fast can hit against the rock, and you do that millions and millions and millions of times over again, and you can get erosion via abrasion and weathering via abrasion of particles impacting the rock. So these are a really neat characteristic feature of that. They're long linear ridges formed by this wind abrasion, and they're often referred to by this term yardang. There's actually some really gorgeous examples of those on other planets too, like Mars. And then finally, amongst physical weathering, there's the organic processes that can result in physical weathering of rock. Things like plant roots and burrowing animals can result in weathering of material. So plant roots are actually really effective at breaking rock apart. So if you start with a small fracture, for example, a plant root can get in there, and plant roots can do similar to what ice does. They can expand and contract and expand and contract as they uptake and release water, for example, and during the days and nights. During the daily cycling, those roots can grow and shrink just a tiny little bit, but enough to cause a stress on that rock and to slowly break it apart. There's actually some really cool recent work by several folks, several researchers who have looked at also the effect of wind and whether wind on the trees cause them to vibrate enough that can actually crack rock. And it turns out that it can impart a significant amount of stress on the rocks as well, which is pretty cool. You can even see in this image on a relatively recent scale, circa hundreds to thousands of years, these structures in Cambodia that are being pulled apart and broken apart by these trees here. So that can be a very effective agent of physical weathering as well. So those are the main ones that we'll talk about for physical weathering. So next I'll move on to chemical weathering. And so chemical weathering, as I mentioned, is the breakdown of rock by dissolution or transformation of the minerals into some other mineral structure, and by changing the chemistry of those minerals. And so the things that influence the rates of which that occur are things like the mineral size, right? So if you had small particles to start with, like we talked about a little bit earlier with the physical weathering, the smaller the particles are, the higher the surface area to volume ratio, right? So the more surface area that's available for whatever fluid is carrying the chemical products that are responsible for the weathering process, the faster the chemical weathering process can occur, right? Composition matters a lot for chemical weathering as well. So different minerals have different solubility in different types of fluids. So it's not just one mineral is more soluble than the other. It depends on what the fluid is actually composed of. And then climate. So the climate can influence the temperature of the water, right? And temperature matters for a lot of chemical reactions. It can influence the water chemistry. Different climate regions have different types of water chemistry of the rainwater and of the groundwater and surface water. The vegetation that's present, so different types of vegetation or plant life can bring with it different types of organic chemicals. Sorry for that beeping over there. That'll stop in a second. And so different vegetation can have, say, organic acids, for example, tannins, etc., that can both promote or slow down the chemical weathering processes, depending on both the type of chemical it is and what the composition of the rock that's being weathered is. Okay, so we'll talk a little bit about some of those things. There's a kind of an interesting little tidbit about chemical weathering. For example, if you've ever been to, say, the beach or out on the Mississippi River, or in any looking at any siliciclastic sedimentary environment, you might notice that quartz is the dominant sediment that is preserved in the rock record as sedimentary rock or as stratigraphy, but also the dominant sediment when you go to the beach or you go to a river. But only 20% of Earth's crust is composed of quartz, so the original material of these granites and diorites and so forth, of the crustal material of Earth is predominantly feldspar, right? And so the reasoning behind that is that quartz is much more resistant to most chemical weathering processes than feldspars, right? The quartz generally does not tend to chemically weather very readily, right? And when it does, it results in silica in solution in very small quantities, right? So quartz tends to not go very, does not tend to go anywhere in the chemical weathering process. It tends to stay behind, versus things like feldspars and amphiboles and olivines, for example, end up weathering much more readily to things like clay minerals, hematite, and so forth. Okay. Sorry, my dog is trying to jump up on the desk here. And you might think about this in the context of the susceptibility of a particular mineral to weathering in a sort of a generalized typical weathering environment. And when I think of a typical weathering environment, I'm referring to something like where water and maybe CO2 are the predominant weathering agents. And we'll talk a little bit about CO2 and how that works in a minute. But you can see here that the typical weathering stability series follows the Bowen's reaction series kind of in reverse, right? That the more mafic minerals, right, are the least stable, right? So the olivines, the augites, the hornblends, biotites, the calcium plagioclases, the sodium plagioclases are more susceptible to chemical weathering than the potassium feldspars, the quartzes, and so forth, right? Muscovite's a little bit of an anomaly. It's pretty susceptible to weathering, although there's some details associated with that, right? But so the Goldich stability series is sort of what you would consider the weathering susceptibility, and it's sort of the opposite of the Bowen's reaction series in a sense, right? So the things that crystallize out of a melt first or at the highest temperatures would be the ones that you would consider to be the most susceptible to chemical weathering first, okay? And I can't let that slide go without showing this dorky little picture, which I absolutely love, of the Bowen's reaction series / Goldich stability series of dogs. So we can go over the three sort of main types of chemical reactions that are associated with chemical weathering. So we'll talk about dissolution, hydrolysis, and the redox or the oxidation reactions. Predominantly, oxidation is responsible for making more susceptible, making minerals more susceptible to chemical weathering. So first off, we'll talk about dissolution. So dissolution of a soluble material will typically occur in the presence of CO2, right? So CO2 is when dissolved in water is acidic, and so it can dissolve rock material, like in this case calcite, right? CaCO3 is calcium carbonate, that's calcite. So in the presence of water and CO2, you will have dissolution or dissociation of the CaCO3 into calcium ions and bicarbonate, right? So that's a relatively common dissolution reaction of carbonate minerals, okay? In this case, one of the key or one very common reaction that takes place in the fluid before it reaches the rock material, right, in order to promote the dissolution of rock, is that you have CO2, which is common in the atmosphere, right? CO2 can dissolve in water, right, and it's based on its pressure in the atmosphere. So if you have higher pressures of CO2 or higher concentrations of CO2 in the atmosphere, more of it can dissolve in the rainwater, right, or in seawater or lake water or wherever, right? And that dissociates, right? So it dissolves in this way, right? You get H2CO3, which can dissociate into a hydrogen ion and a bicarbonate, or two hydrogen ions and carbonic acid, right? And both bicarbonate and carbonic acid here are acidic in the sense that they release these two hydronium or H plus ions, which can then be available to dissolve rock, right? So H plus is a very effective, right? That's what an acid is a hydronium ion, and that's what is very effective at dissolving rock, both carbonate rock and silicate rocks as well, right? All rain, because of this, is mildly acidic, a pH of about 5.6. Remember that a neutral pH is about 7. And that's because there's CO2 in the atmosphere. That CO2 is dissolving in the water, in the rainwater, and becoming carbonic acid, right? The next type of chemical weathering reaction we can talk about is hydrolysis. This is what happens when minerals react with water to form other minerals, right? So rather than being dissolved entirely, the mineral can react with the hydronium ions in the water to alter the mineral compositions, right? So they can replace other ions in the mineral's atomic structure. Feldspar, which, as we mentioned earlier, is the most common mineral type in rocks on Earth's surface, does this readily. It reacts with the hydronium ions in water to form a secondary mineral like kaolinite, so it reacts to form clays by this reaction here. So this is the reaction of orthoclase feldspar and hydrogen ions in solution, and that forms kaolinite clay with dissolved silica, right? So this silica gets dissolved into solution, right? And potassium ions, which also get dissolved into solution, okay? And you can see the same kind of reaction occurs for anorthite, a calcium feldspar, and results in kaolinite clay and calcium ions in solution, okay? And this is the predominant mechanism by which seawater chemistry becomes what it is, right? So seawater has calcium ions dissolved and silica dissolved in it, and that is because of these Feldspar hydrolysis reactions that result in the clay, the kaolinite that gets left behind, if you will, during the weathering process, and the soluble components that then get, flown. They flow down the river, for example. And then finally, we'll talk about oxidation reactions, which result from the loss of an electron from an element like iron or manganese, and this typically results in the formation of oxides or hydroxides, right? The loss of an electron in this particular reaction here of iron, right? So if you have iron 2 plus, and you can add oxygen to that, and you can get Fe2O3 here, so you can change from a ferric to a ferrous, ferrous to a ferric state, which can result in the increasing solubility of an iron mineral like that, right? So this is a more soluble state than, say, just base iron, for example, or magnetite may be less soluble than hematite, for example, as you continue that process further down. Okay, so those are sort of the different types of chemical weathering reactions that can take place, and can result in both solutes that get washed away, and as well as changed mineral types, if you will, or changed mineral structures being left behind in the at the weathering site. Okay. As I mentioned before, both chemical and physical weathering processes take place at varying rates across Earth's surface, dependent on a number of things. Two of the big controls or drivers of the sort of weathering process disparity across our surfaces, the rainfall rate, right? The amount of water that is being provided to the system to do things like dissolution, oxidation, hydrolysis reactions, right? So the more water that is flowing through a soil, for example, the more chemical weathering you could expect, right? And the same thing is true for temperature, right? So the warmer temperature, the warmer the temperature, usually those chemical reactions proceed faster in higher temperature systems, right? Whereas in the colder temperature regions, you're more likely to have those temperature fluctuations that result in freeze-thaw cycles and so forth, right? So as you can see on this plot, the sort of lower rainfall, lower temperature, I apologize that the axes are a little bit weird on this. So temperature is going from cold to warm on mean annual temperature here, right? And rainfall is going from low to high here, okay? So if you're looking at this plot, right, the physical weathering sort of sweet spot is up here in relatively low rainfall, relatively cold regions, right? If you get too cold and too low rainfall, the processes aren't, the freeze-thaw cycles aren't as pronounced, right? There's not enough water to get into the cracks and promote those kinds of things. So you actually get slightly lower physical weathering at some of these more extreme ends of the system. And then as you go into higher rainfall, warmer temperatures, think the tropics, right, you end up in a more strongly chemical weathering driven environment, right? So some examples of places where this might occur, and these are very approximate, right? Alaska might be up here in the more physically weathering dominated areas. Boulder, Colorado is sort of somewhere in between, right? It's warm some of the year, but doesn't get a lot of rainfall, right? Places like the Altiplano in South America receive very little annual rainfall, have relatively warm temperatures, but there's just nothing to do the weathering to promote the weathering processes, so you end up in regions where you have very little chemical and physical weathering processes. Whereas in the Amazon or New Orleans, you're probably fairly strongly chemically weathering dominated regions. Okay. So those are important concepts to think about when you're thinking about what type of weathering is resulting in both how much sediment is being produced and what types of sediment is being produced. Are you predominantly forming clay minerals and solutes, or are you predominantly forming broken down chunks of the original rock, right? Okay. And the degree and type of weathering that takes place in a region also strongly influences the size of the material that results from that, right? So ultimately what we're interested in as stratigraphers looking at the rock record is what these clastic particles are that come down from the weathering regions into our depositional region, right? And so the size of the clasts can be somewhat indicative of the type of weathering process potentially that's going on in the upland regions, right? So for example, with boulders, those are typically formed from directly fracturing and jointing the parent rock. You're not breaking down the mineral grains into individual components, right? Whereas sand is typically on the order of, my dog's sneezing back there. Sand is typically on the order of the same scale as the average mineral grain in a granite, for example. There's actually some really interesting old studies that were done in the 50s and 60s about that, where it was found that the average grain of sand in the world's rivers and beaches is about 300 to 500 microns in diameter, and the average quartz or feldspar crystal in a granitic pluton is about 500 microns. And so those sand is predominantly made of just breaking down individual component mineral grains from the granite directly and then transporting them, right? Silt predominantly forms due to abrasion of those particles. So as you transport them, or as they are abraded by glaciers, for example, or in aeolian settings from impacts of other sand grains, you tend to break those sand grains that were the original mineral size down into silt. Okay, so you take a 300 micron sand grain and you break it down twice, you end up with silt. Right? And then finally, the clay-sized particles tend to be actual clay minerals on average, and those are formed from the residue of the sort of, after all of the unstable or soluble elements have been weathered and removed, right? So you end up with the kaolinite clays and so on and so forth, or the silica, ooze or whatever is left behind typically tends to be smaller grained clay-sized particles, okay? And we define these particle sizes by what's called the Wentworth scale, which is shown here, okay? And this will come up throughout the course and probably throughout much of your geologic career, and we define them based on very specific size intervals here, and those intervals are given here on the millimeter scale. These are close but not perfectly exact. It's 0.0625, for example. So you can find other more precise. And when we give you your lab on grain size analysis and particle observation, you'll get a much more precise version of this. But these are tied to another size classification that we refer to as the phi scale. And I mention this because it does get used quite a lot in the sedimentologic universe. And all it is a logarithmic space representation of these grain size classes. So if you look at these, they can get a little cumbersome to be 0.004, 0.06, 0.25, 0.5, 2, 2, 4, for example. So if you put these on a log base 2 scale, you come up with round whole numbers with even numbered breaks between all of the size classifications. And that fee scale is defined this way. You'll use this in the lab, and it will come up throughout your geologic career if you're ever doing a site characterization, or if you're measuring section or working for the Corps of Engineers. This will come up again and again. So this fee scale is defined here. Phi, the Greek letter here, is minus log base 2. So normally when you put in a logarithm in your calculator, it'd be log base 10, or a natural logarithm, which is like 2.3 something. This is using the base 2. Okay, so every gradient, or every change, is a factor 2 different from the next one, right? Right, you can see 0.0625. There's another classification break in here at 1250, and then 0.25, 0.5, so on and so on, right? And so it's minus log base 2 of the grain size in millimeters. Okay, so that's important. These are all millimeters. The minus is there, just this is just for your information, but the minus sign is there for sedimentologists primarily, so because we're typically dealing with sand and mud size things, clay and silt. And it was done so that these would be positive whole numbers, and then the big stuff that we don't use that we don't deal with all that much as sedimentologists, like boulders, are all negative numbers. You might see in the soil science literature quite a lot, there's the psi scale instead of the phi scale, and it's the same base, but instead of a negative, it's a positive here. So it'd just be the reverse. You'll see that sometimes. I just wanted to make you aware of that. We won't deal with the psi scale in class, though. Okay. So that's the end of our weathering discussion for this class. I've posted this discussion question to kind of get you thinking about, the temperature versus rainfall, versus potentially questions about, acidity and so forth. Is think about the timeline of Earth's geologic history. So everybody's probably taken an intro geology course where you've talked about, what Earth's atmosphere was like at the beginning versus now, and when things were warmer versus colder, right? There were hothouse times, greenhouse times, there were icehouse times in Earth's history. And so I just want you to think, I'm not going to expect a right or wrong answer for this question, but I want you to think about that timeline from Hadean to present all the way through, and think if there were times in Earth's past when physical and chemical weathering rates would have been the highest and would have been the lowest. So the highest physical rates, the highest chemical rates, the lowest physical rates, the lowest chemical rates. And why do you think that? I don't need to, a ton of information on this, but if you think, oh well, there was this greenhouse time, and that probably was blah 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 blah, let me know. Okay. So the way we do these quizzes is you can submit your answer in Moodle. Associated with this section 1 in the course documents in Moodle, there will be a little green box that says quiz. I think it says weathering quiz, and you'll just have a little short answer box that you can fill in and write in your answer. So by next Thursday at I guess 11:59 p.m. is when that closes. So go ahead and submit that. And so we'll break here, and the next lecture will be a pretty short one, and I'll just talk about the erosion and removal of material from its host location. All right.